Welcome, everyone. This is the CCOM-OE seminar that is given every Friday. This week's speaker is Dr. Morrison. He's a senior ocean engineer at the Woods Hole Group. He graduated from Harvard University with his BA in engineering and applied science and electrical engineering, and then later received his MS in oceanographic engineering from the MIT HUI program, and also later received his PhD from the same program. Dr. Morrison has experience in instrument development, design of oceanographic systems, and underwater vehicle control. He is giving us permission to interrupt him during the talk. So if you have questions, feel free to either raise your hand or enter the Q&A chat as well. And we will also be doing the Q&A session at the end as usual. So with that, I'll hand it over to Dr. Morrison. Thank you for coming and welcome.
Okay, thank you very much. Thank you for having me. I have been looking forward to this talk since last April when we were going to try to do it actually up in Durham, but reality intervened. So today I'm going to talk about current profile measurements we've been making in the Gulf of Mexico. I will probably tell some stories along the way and try to frame this program appropriately. As Alyssa mentioned, I work for a company called Woods Hole Group, not to be confused with Woods Hole Oceanographic, although we have many affiliations with them. Woods Hole Group is actually a subsidiary of CLS that is largely a satellite remote sensing company homeported in Toulouse, France. But Woods Hole Group was recently acquired by them, but has been around for 30 or more years. Originally was a spin-off from Woods Hole Oceanographic, thus the relationship. I trust everyone can hear me. I haven't been adjusting my mic volume, but if I'm not coming through clearly, I will trust Alyssa and Ann to let me know. I'm going to appeal to this phrase, this quote from Isaac Asimov, among others. This to me is strong motivation for what I do as an engineer. And I've always, ever since I found it, I've liked this quote. The most exciting phrase to hear in science, the one that heralds new discoveries, is not "Eureka, I found it," but just kind of scratching your head. That's funny. The Eureka to him was, I found what I was looking for, which is great. But if you are prepared and you are making observations and you see something you're not expecting, that's funny moment that you have to be prepared for. That's when something new is discovered and something interesting goes on. And that can be a very exciting kind of thing in science. And I've often thought of myself as an ocean engineer and getting to stick my nose into everybody else's science and engineering, because you can't do things without the engineers, that one of the things I do is enable that moment for other researchers. And before we get on to these measurements in the Gulf of Mexico, I am going to offer you an example from my own career. What you're looking at here is a profiler. This was first developed in another shape at HUI back in the 1990s. It got spun off commercially. I got involved with it in the late 90s. You're looking at the right there at what we might call serial number 0. That was sort of the test one as we were trying to develop this and make it work. And it's basically a robot. It just crawls up and down a cable. It can cover, roughly 2,000 meters on the cable repeatedly. Cumulative distance can get up near 1 million meters of profiling. And it just goes up and down on a schedule carrying a CTD and a current meter. So here's the story. For many decades, still going on now as far as I know, oceanographers kept watch and did CTD casts at a site near Bermuda. And they would go out once a month in the Weatherbird or the RV before that, research vessel RV. But that was all anybody could afford, once a month, because research vessels are expensive. at least on the budgets of research institutions. And they acquired a time series that is incredibly valuable. It went on for literally decades of once a month, and they go out and do a CTD cast. Then we built this, put it on a mooring out at that site, and it went up and down once a day. And immediately, the first data set, the people who were using this found these anomalies, and they were eventually able to interpret them as mid-size eddies that were propagating through, mid-size means tens of kilometers in diameter, propagating through at that site at 1,000 meters or 1,500 meters depth, no surface expression, and they would propagate through in the space of a few days. And in decades of once a month sampling, not once had they ever caught one of these things, even though they were ubiquitous at that site and other sites. They blew through all the time. So there was that head scratching, that's funny moment of finding something new, completely unexpected, but completely enabled by new technology and new ways of being able to look at the ocean, look at the earth, and make measurements you just couldn't make before. And in this case, it wasn't that we didn't have CTDs, it was really that we simply could not look often enough until we built a device that could do it for us. So onto the topic of our program in the Gulf of Mexico. Here's a Google Earth look at the bathymetry in the Gulf of Mexico. Yucatan down here, which will come up later, Cuba, Florida. You'll all be familiar with the Gulf Stream that goes up along Florida and off into the Atlantic. Bathymetry here, if you see this feature, some fairly steep bathymetry called the Sigsbee Escarpment. And if we go to the next slide, this is the loop current. And what's there in bright colors is sea surface height. I will presume at least most of you are familiar with pictures like this. And what's happening here is that what you're seeing in this dark patch is water that is roughly a meter higher relative to some standard reference than the water that's off in some of these patches. And of course, when you've got that sea surface height difference, which is something like a meter, you're going to have in our rotating Earth, Coriolis and all of that, spinning currents. And what really happens here is you have the North Brazil current well down to the right, comes up into the Caribbean, kind of disperses, isn't trackable, but comes together and goes here through the strait between Yucatan and Cuba. And generally speaking, comes up, loops around, and goes out through the Florida Strait and is suddenly named the Gulf Stream. So this feature is called the loop current. It tends to pinch off eddies, and it is in the process of pinching off Eddy Yankee. Side story, part of Woods Hole Group is the former Horizon Marine, HMI, and because they're the ones that have traditionally tracked this feature for oil companies operating in the Gulf of Mexico, they get to name them. So all of the eddies that have gone through here have been named by us at this point. Anyway, what's happening is that you've got an eddy forming. It's going to pinch off here where my cursor is. The loop current will then be shorter and blow right out here and become the Gulf Stream. And this eddy will keep rotating and eventually move off to the west, but it will migrate in an unpredictable way. This is the previous eddy still spinning off here near the coasts of Texas and Mexico. All right. Here's the interesting thing. And I should add, there are these counter-rotating eddies off here that are spinning in the other direction. The loop current and the loop current eddies' speeds exceed 4 knots regularly. Those speeds penetrate several hundred meters. It's not just a surface thing, but they get going at a speed that is more than sufficient to disrupt drilling operations, drill ships, platforms, things like that. So tracking this movement becomes an important safety and operational issue for the oil and gas industry, which is pretty active in the Gulf of Mexico, as we see in this next slide. So here's Florida over here, Gulf Coast, Alabama, Mississippi. Here's Louisiana, the Mississippi River's coming down here, Texas over here. And all of these little blocks in here are lease blocks. The US government will lease them out to operators, oil companies like BP, ExxonMobil, Shell, names you have heard. And all of these lines in here and more are oil pipelines and gas pipelines and things on the floor there. Well, how much infrastructure is out there? Over 3,000 active wells. This includes fixed platforms, gravity platforms, tension leg platforms as you go out into deeper water, semi-submersibles, giant drill ships, on and on and on. 3,000 of these facilities. All right, something like 25,000 miles of active pipeline on the bottom of the ocean there, and another 18,000 miles of out of service pipeline. Much of the, well, all of the active pipeline, excuse me, is pumping oil and gas and things like that. You've got all these facilities, there are people on them, they're actively drilling and doing things to move oil around. And however you feel about the oil and gas industry, and I myself am a huge fan of wind and tidal and all these other things, but however you feel about them, that amount of infrastructure has to be protected, and you have to make sure it's operated safely, and sometimes it isn't, sadly. So it's important to understand features like loop current to try to protect these facilities from getting badly hurt, damaged, knocked over, and then you've got an oil spill or something to deal with, which would be bad. We are trying to avoid that. As Alyssa said earlier, if you have any questions, feel free to interrupt. It's fun for me to interact and address concerns and questions. All right, going on. So back in the middle aughts, 2004, 5, and beginning in 6, government agencies, starting with what was then the Minerals Management Service, MMS, declared that all oil and gas installations in the US waters, Gulf of Mexico, that were operating in quote unquote deep water, anything more than 400 meters, or near significant bathymetry, remember the Sigsbee Escarpment, so anybody who's operating near this feature would be required to make speed and direct or measure speed and direction profiles from the near surface to near bottom or 1,000 meters. They would also have to make near bottom measurements if they were working somewhere deeper than 1,100 meters. And they needed to return these measurements in 20-minute averages, at worst, every few hours. And at best, every 20 minutes, they should be sending in a new ensemble to a government database. In the aftermath of the Macondo Deepwater Horizon spill in 2010, MMS was broken up into the Bureau of Ocean Energy Management and the Bureau of Safety and Environmental Enforcement, BOEM and BESI. But these notice to lessees, NTLs, stayed in place and were augmented. So all of these installations are required to make measurements. And what's expected is roughly 1,000-meter profile, speed and direction at a whole bunch of depths, from wherever they're operating at the surface down to the bottom. There are niceties on that as shown in these bullets, but the basic thing is thou shalt return current profiles, or you don't get a license and you're not allowed to operate and look for oil and drill and things like that. Hope all of that's clear, but what this has meant is that since the oil companies, and I should add, the operators, the oil companies, like, for example, BP, who have a lease on these blocks, then turn around and hire a company like Seadrill, who own drill ships, and lease the drill ship to go and do work. And then all of them turn around and hire a company like Woods Hole Group, who are consultants and do field work to do the oceanographic measurements, because they don't have that expertise. Their expertise is drilling or oil production or things like that. So they pull us or some of our competitors in, and we're the ones who make these measurements for them. And I will be talking now about how we do that. This is my operating environment when I go out to sea or when I'm working with them remotely. And I just want to give you a sense of the size of these vessels. This is the West Auriga, owned and operated by a company called Seadrill. They are leased to BP. As an example, this crane right here can lift something like 85 metric tons, and it's not even the big crane on board. I will point out that there's a little bit of island in the background here. That is the island nation of Mauritius in the southern Indian Ocean. And this was when the ship had just been built, and it was coming from Korea via Singapore to Mauritius and eventually around Africa and into the Gulf of Mexico, where it operated. But we were trying to get our equipment installed before they got there. So size-wise, helicopter landing pad up here. You see this module in white and lifeboats, but it penetrates down into the ship. This module is a 7-story office and hotel complex. The rest of the ship is for the drilling. Overall length is about 250 meters. So you would have no trouble at all dropping 2 soccer fields on this, and you'd have space left over. These guys are just huge. We operate our little rig on what's called the tensioner deck, actually on the other side, but we're up at about that level, if you can see my cursor, and have to dip stuff in from 20 to 30 meters in the air. We're not able to get right down on the deck, closer to the water. It's very unlike a research vessel, and I will pull up this little bullet point. I do not know how many of you who have actually gone out to sea on a research vessel, but the numbers are different. Instead of having a dozen people on board, you have anywhere from 150 to 200 people on board, working 24/7. On board and being deployed, anything up to 10 or 15 kilometers of drill string and riser. I mentioned earlier the quote unquote expense of renting a research vessel, which, is measured in tens of thousands of dollars, I suppose, generally. The day rate for that drill ship is in excess of $500,000. And there's another $500,000 of daily operating costs. So roughly speaking, every 24 hours, there's $1 million in play with one of those things operating. We don't get to any working deck that's close to the water. The oceanography is required by regulation, but it is not the focus of anybody except you when you're out there. The rig just wants you to finish your maintenance or installation or whatever so you can leave, except when they need your help. And Alyssa is going to ask me about that at the end, and I will try to tell you a very amusing story. They're huge, 230 meters, 250 meters length overall. Research vessel, more typically something like 30 to 50 meters. I think the largest research vessel I ever saw was a Japanese RV that did manned submersible ops, and it was 100 meters. So really not even close to these things. I'll bring up a couple of slides next that show some of the oddities we put up with to be able to operate in this environment. But there are many, many safety qualifications that all of us have to go through regularly. And some of them are one and done, some of them are every year, some of them are every couple of years. You have to have personal protective equipment when you're out there: steel-toed boots, heavy coveralls, impacts resistant gloves, safety glasses, hard hat. Your hard hat has to be tied to your coveralls so it can't blow off in the wind. Plastic overboard is a huge no-no. On and on and on. All the clothing you wear has to be fire retardant, and there are just absolutely no exceptions to these rules. So one of the most, strangely enough, enjoyable bits to me of safety qualifications is called HUET. That's Helicopter Underwater Egress Training. This is part of the pool training. This is a simulated helicopter cockpit, or well, not the cockpit, but the cabin. Here's a safety instructor. Here's a safety diver. Here's a couple of students. I have been one of these guys many times. And what they do after you've been put through the classroom, and you have to do this every 3 or 4 years, is you suit up, get in the pool, you climb into this thing, and then they hoist you up about 10 feet in the air, drop it into the pool. It sinks rapidly. It's filled with water almost immediately, so you're holding your breath. And in a very controlled way, with a 4-point harness on you, as you would have in the helicopter, you have to push out the windows, as you would in the helicopter, and doors, orient yourself, release the seat belt, and get out the window and get up to the surface. And if you're able to do that 5 times, you pass. And if you aren't able to do it 5 times, they make you do it again until you have. And just to make this even more interesting and exciting, after you've mastered doing it as shown here, they crash it into the water and sink it and flip it upside down, and you still have to maintain your orientation. You can see these seats are now upside down. Push out the window, get out, and get to the surface. And if they're really feeling their oats, they might turn out the lights. So if you want to work offshore, you have to go through this. But I will tell you that it is actually not too terrible. They are very good instructors. They are interested in training you, not failing you. And they really hate it when somebody drowns. So it can be a lot of fun. Like I said, I've had to do this a few times. I probably will do it maybe once more in my career, and just in case I have to back up some of my young guys. But they do a very good job going out to sea, and it's kind of nice to not be that person anymore. But the HUET training is fun. Once you get on board, and this is just a little bit of the operational environment at a more personal level, there's a picture of me after a shift in the locker room or here. It gets really hot out there. I remember a trip not in the Gulf of Mexico. We caught up with a rig, a drill ship in Trinidad, rowed it down to offshore Suriname. What's shown here in the picture, aside from me, is the locker room that's in the basement of that multi-story office and hotel complex. You were not allowed to have dirty clothes in there. So there's a locker room and kind of an airlock arrangement where you change into your PPE. You can see my, coverall, sweaty t-shirt. Can't see my boots and gloves, but they're floating around. But you kind of airlock in and out to be out on deck. And anyway, we were down in Suriname, and I was out on deck. I had one guy with me, and we were soldering wires on a cable and making a splice so that we could communicate between the PC and the instruments. We'll talk about the instruments in a moment. And so it was kind of close work. I was looking at wires, right in front of my face and operating a soldering iron and things like that. And so this is another aspect of getting a little bit older in this game, but I had to wear my prescription glasses instead of my safety glasses. so I could really see what I was doing. And therefore, for safety reasons, I had put on a pair of goggles over my prescription glasses. It was well over 100 degrees and humid off of Suriname. I have seldom been in such heat and humidity. And I was ensuring that everybody was drinking water regularly, but we were sweating faster than you could drink, quite literally. And as I was soldering, I leaned over to look closely, and my vision suddenly went fuzzy. I thought, my God, am I heat stroke? I need to get into a cool room. What's going on? And then I realized what had happened is when I leaned over, all of the sweat dripping off of me had filled up the goggles, and I was looking through water, very salty water. So I tipped that out and was able to finish soldering, but it was really that hot and humid, and we had to work out on deck. And there are times you come off a shift and this is what you look like. But we try to get the job done regardless. Okay, so let's talk about one of these systems. We use instruments called ADCPs, acoustic Doppler current profilers. There'll be a picture of one of them later, but our basic idea is that we're going to hang a sled of some sort, a steel frame, off of the side of the ship. So we're going to maybe need an A-frame and some winches and things like that. And we'll lower this down so we're below the keel, and we'll have two ADCPs on it. One of them's going to look up towards the surface. I'll describe how these work in a moment. And one of them's going to look down. And this will be a relatively short range instrument because we're only going to be 30 to 40 meters down. The keels on these things are at about 11 meters, and then there's 6 thrusters that extend down another 6. We want to be below that. And then this is a long range instrument. It has a range of about 1,000 meters. So it's looking down into the ocean quite a long way. How do these things operate? Well, there's generally 4 transducers. You're seeing a pair of them in a sense here, where one of them's shooting out a beam this way and the other shoots out a beam that way. Those 2 beams define a plane, a vertical plane, and it's a little hard to picture. I don't know if can all of you see me, or are you just seeing the slides? I guess you're just seeing the slides. You could imagine 2 other transducers putting up similarly angled upward-looking beams, but in an orthogonal vertical plane. Anyway, if you think of the vertical plane here, each of these transducers puts a short ping in the water and then listens for the echoes. And as you listen later and later in time, you're hearing an echo from further and further away. Simple enough. All right. If we assume, I'm going to go to the downward looking now, but if we assume that the flow of the ocean is going from left to right here, and that it's pretty much the same horizontal flow in this beam at a certain distance, a bin, and in this beam at a certain distance, a bin, the water coming along in this direction is going to compress the echo. There's a Doppler shift. So this echo at a certain distance is going to be slightly higher in frequency. This echo, because of the angle, is going to be stretched out a little bit. It'll be slightly lower. So if you look at the difference in the Doppler shifts, which is going to be proportional with a sine theta in there to the speed of the water at that depth, you can calculate the speed. So I've now got a speed at that depth in this plane. Now I look at the orthogonal plane from the other 2 transducers, and I can get a U and a V at different depths. And that's how I build up a speed and direction profile from these instruments. Feel free to ask me about it now or later, but that's the basic way it works. So we're in a general sense, when we built the first system we built along these lines, this is what we were looking at. You know, an instrument sled, maybe an articulated A-frame to make it easy to launch and recover. Articulated just means we can pull it in or let it out. um, electromechanical cables, a slip ring, things like this, and the winches. And, as you see in the bullet points, and I just described, an upward looking 300 kilohertz that has roughly 100 meters of range, so that's more than enough, and a downward looking 38 kilohertz that has the 1,000 meter range. Of course, we're going to need a PC to talk to the instruments, and remember that this data is supposed to be coming back home in real time to the government database. So that PC needs to be on a network out on the rig so that we can send the data. The people on board would like to see what's going on, so we need to think about some way of pushing text and graphics and textual information about what's going on around the ship and things like that. So the first time we built one of these systems, 10 or more years ago, in my case, those were some of the things we were thinking about. Then we started to look at what our competitors had done. And this is a picture of an early system that somebody else had made that to me was just an abomination. I was just like, you're kidding. This is terrible. It's hard to operate. It's grimy. It is incredibly labor intensive to use. It is not safe for personnel. It breaks easily, and things like that. On the other hand, it's really, really cheap. And the people who are operating it on board, the poor crew, are not the people writing checks. And the accountants like things that are cheap. So this is what we were competing with. The way this works, and I'm going to back up one. This downward looking 38 kilohertz instrument, before we got on the scene, has a giant transducer, weighs 600 pounds, this red thing. And then there's a cable with 50 conductors in it, jacketed, that comes up to a deck box. And the way these systems were set up, they had little air tugger winches with wire rope, and some poor guy would have to sit at the edge of the deck here with a fall harness on. And as they let the instrument out over these blocks, the wire ropes paying out from these two little air tugger winches, he had to sit there with a huge bag of tie wraps, plastic tie wraps, and tie that 50 conductor cable to the wire rope as it went out. And then when they have to recover it, he's got to carefully cut each tie wrap and start hand coiling the 50 conductor cable, which turns out to be incredibly fragile, also expensive. And it was always getting cut by whatever sharp tool they were using to cut the tie wraps. And then it would take weeks and weeks and weeks to get a replacement for it. And it would cost $10,000 every time or more. It was crazy, but that was the design. And that was what our competitors were using and selling. And just the personnel safety issues to me were crazy. It took hours to get something in the water, get it back out. Because this A-frame is not movable, somebody had to literally sit here on the deck and push the thing overboard. They would pull it up, but it wouldn't clear the lip here. And they'd have to push it out with their feet while somebody else lowered it and hopefully not catch their feet. And then when they were trying to recover it, they'd pull it up here and they'd have to get ropes on it and have a couple of guys pull in, and then they'd try to lower it onto this platform. So to me, it was just appalling. I was coming out of, among other things, some experience with ROVs and much more advanced systems. And I was just appalled. I could not believe how unsafe this was, but this was the pervasive design at the time. So Wood's whole group was responsible for a number of innovations, but everybody else still goes with stuff like this because it is really cheap. And it makes it very difficult for us to sell a much safer and more easily used system, but we are able to do it on occasion. So here's some of the things we innovated. Instead of just the transducer, This thing is about 1 meter in diameter. This is a steel plate it's being bolted to underneath. We talked Teledyne RDI into putting the deck box boards into what's called the UWEA, the Underwater Electronics Assembly. What does this mean? It means the fragile cable is all here on the sled, and no tie wrapping, cutting and uncutting and putting it on necessary. We just get it in here the first time. We wrap garden hose around all cable that is underwater to prevent fish bite, which is a real problem, believe it or not. And now, from this UWEA, we only have to ride up with 7 conductors to be able to do serial communication and power. And our innovation was to put that in, you'll see this in a moment, but in armored electromechanical cable. So this cable now has the conductors inside it. It's not just wire rope. And it is both load bearing and power and communications bearing. Here's the Workhorse 300. This is the upward looking ADCP. There's a cap on it right now, so you can't see the transducers. Tipped out, so it's a little bit away from the boat. You'll see this more clearly in a moment, but this is the sled. All right, you can see a little bit of the A-frame here, a little bit of one of the hydraulic rams. And if we go on to the next picture, these winches have slip rings on them so that we're bringing, again, you can't see it yet. I'll get on to another picture, but these are carrying the load, the mechanical load, as well as the electronics. There's a mechanical termination there, cable going into the electronics on either side, but it comes from the slip ring and then can come back to the computer through the harness on the ship. Just sort of to let you know, with all that hydraulics, you need a hydraulic power unit, an operator control stand, but this keeps personnel away from the hazardous area. This can be away from the edge. And here's the whole thing, a slightly different view. I'm not going to go through all of these parts, but if you're curious, I can talk about it at the end. But here we have the UWEA. Here we have a baby ocean that the transducer's sitting in. The Workhorse isn't in this picture right now, but this is the sled. The sled can be picked up, right, over these sheave blocks. Here's the cable, all right? And then you can swing the A-frame in and lower it into this cradle, which is designed to hold the sled safely and the instruments so nothing gets hurt. You just pull it in on the winches. Your control stand and HPU can be off to the side. You just run hydraulic hoses. And then now, instead of needing a team of 5 or 6 or 7 operators to run the air tuggers and safety observer and somebody, probably 2 people out on the edge doing the tie wraps, and 2 or 3 hours to get it in and out of the water, you need 2 people. One of them stands by the control stand and operates it. One of them stands by the railing, behind the safety railing, as an observer. And you can launch and recover this both in 15 minutes to do both operations. I think our record's about 8 minutes. It's that much faster and more convenient, and nobody gets in harm's way. This was the first of our designs, and we went through several iterations. Next thing we added was a level wind so that the cable was more protected. You didn't have any danger of it going kind of over itself and getting a tight bend. We also changed cables. There are more conductors in this. That was partly just because we found ourselves building a single wire system where we needed enough conductors for 2 instruments in 1 wire. And we decided we'd just use the same cable for all of our systems. We've got a number of these systems now out. You can see here in yellow is the hydraulic ram that moves the A-frame. The power unit's back here. On this ship, you can't see it, but the control stand's well off to the left, where you've got a clear view of the water. We are rather high off the water, unfortunately, but that's where they put us. Anyway, we've got a number of these, and I've been pretty happy with this version of the system, but there's an awful lot of moving parts. These switches often break when it comes to the level wind, and we have to replace them and things like that. And so we got thinking about, could we improve on the level wind? And we ended up, for a system, designing our own winch. It's a bit bigger than those blue ones, but we realized we don't need to have more than about 80 meters of cable on here. That gets us down the 20 plus meters to the water. It gets us the 35 meters below the surface. It still leaves cable on the drum. And here's the thing. We made a drum, or our fabricator did, where there's a single groove. It's a helical groove, you know, like a thread all the way around. And because of that groove and this roller, which keeps the cable from getting out of the groove, it's not pinching the cable, but just prevents it from jumping. That's the level wind now. So it's just this one roller on a couple of bearings and the groove. And that design is the one we're using going forward. Almost no moving parts, simple, easily behaved, nothing the operator has to get a hand or a push pole into to keep this lined up. No need for a manual override on a level wind or anything like that. This goes smoothly every time. And that's a winch design we came up with ourselves, and I am quite pleased with it. Here is that system fully fabricated at our fabricators. You can see before it's been in the water and started turning colors, but that's the 38 kilohertz transducer, phased array looking down, UWEA, our winch design, nice big A-frames so that we can get well out away from the ship, the cable, shiv blocks, and this is ready to go. You take this out in the ship, weld it down, weld down the HPU, and you are good to go. The rig that this went onto was the Helix Q5000 semi-submersible. To give you an idea of how big this is, again, here's the helicopter landing deck, 400 metric ton lift capacity crane. You can't see the living space, it's on the other side. The deck area up here would be sufficient for 2 soccer fields side by side. This little red thing here, this tiny little A-frame, that's not us. That's that is for one of the ROVs. And this platform, oops, there's my cursor up here, with our A-frame on it, too tiny to see from this distance, but that's where we are. And we have to lower things all the way down past the pontoons. Here it is on board during installation. We're out on that cantilevered platform. A couple of other views of it from, I think I was standing up on the helicopter deck looking at this, looking down on this from on the right. A couple of other views just to show you how nice it looks once we got it out there. And I had mentioned earlier, but you can't have the instruments without something to control them. So we had to write a lot of software. This is the back of the rack, system control PC, some monitors. Here's the monitors at the front. I'll show you a close-up of some of this in a moment. Number of different modules to convert. For example, the VGA signal is converted to video to go out to the closed circuit TV, which is ubiquitous around the ship. So that was a way to show one of our monitors pretty much anywhere, including the bridge and the drill shack, people who wanted to see it. There's other converters here that are going, for example, in our electronics enclosure out on deck, we convert the copper signals, the serial, to fiber optics. And then this little blue module takes the serial the fiber optics, converts it back to serial or network or whatever, and plugs it into the PC. So we are talking directly to the instruments that are hundreds of meters away from where this PC is in the accommodation space. Just an example of the display software that we wrote. This is an operator control panel sitting on one of the monitors. This is a time series showing speed and direction. I will explain it in a minute. This is a single profile. The red, depth from the surface down to about 4,000 feet. They're operating in the US Gulf of Mexico, so they like knots and feet as opposed to meters per second and meters, but I did put meters per second, or sorry, meters down the other side. But that red profile is showing speed, all pretty much below a knot. We went from 0 to 4 knots on the horizontal axis, but that's adjustable. And then the blue dots are showing direction, where 0 is north, 90 is east, 180 is south, and on the obvious, so you can see what direction things are going. Same information, but a time series over here on the left. So again, from the surface to 4,000 feet, showing depth. The color bar shows you how fast something is going. So it's a little faster up near the surface, fairly slow down below. And then the color bar down here is showing you direction. And the features you're seeing here in direction are inertial oscillations. I am glancing at my watch, so I'll just tell you that inertial oscillations are ubiquitous in the world ocean. They're hard to see unless the regular current is very, very slow, as it is here, almost nothing happening at this site. And they are sort of a rotary thing. If you think about at a given depth, looking across over time, what you're seeing is that the flow at that depth is spinning. It's looking north, then looking northeast, then east, then, whatever. And a little bit above that or a little bit below it, it's doing the same thing, but at a slightly different phase. So this whole direction edifice is spinning. This is the main display. We're showing them. So you see that speed and direction, most recent profile going on. There's some metadata for them up here. And these guys often like to see textual data, so we provide it in this way. This is output from the workhorse, so speed, direction at different depths. This is output from the downward looking 38. So again, depths, speeds, directions, there you go. But this is all software we wrote. Actually, this display software I wrote. We had somebody else writing the glue software that pulls it all together, and yet somebody else who was writing the software and firmware that communicated with the instruments and pulled all of that data into the PC, where the glue software did things with it and FTP'd it off to the National Data Buoy Center. And that glue software also made files for this display software to access and read and make pretty pictures that are relatively easy to interpret. Variations on a theme. Other systems we have built have had a sled, again, going up and down a rail in a moon pool. This is a different instrument, 75 kilohertz, but this sled could be pulled up and down on these rails that went from up on the deck near to a moon pool or into the water on the moon pool. Here's another, this was done on, let me think, the Pacific Santa Ana. They would normally have had an ROV here. So there were a couple of pins, large pins down here well below the water line, which was around here. And what we did was fabricate these steel rails in sections. This sled would go up and down that with a cable trailing behind, a winch and things up here, and then the cable would go off to a PC somewhere. We put an enormous effort into designing these rail sections. Roughly, I forget, I think 30 meters overall length. And I took all of this out myself, acquired a rigging crew out on the rig, and we were able, because we had a good design mechanically and because we had worked out an installation procedure, this entire arrangement hit those pins on the first shot, and this whole thing went in less than 3 hours. We also do moorings, and this is schematic of a mooring, not to scale, 1,400 meters of water. This has been out with yearly servicing for 7 or 8 years now near the Mad Dog platform. Similar in many ways. There's a downward looking ADCP here, an upward and downward looking pair at 500 meters, a single point current meter 30 meters off the bottom, inductive and acoustic telemetry, satellite telemetry, comes down to a website at our facility, and all the customer has to do is log into the website from pretty much anywhere in the world, and they can see what's going on, whether they're on the rig or in their office. So data delivery in real time, all of the things we had talked about. I'm going to go a little bit faster at this point. So was this program to acquire all this data successful? We got paid at one point to look at that database and found there were horrible metadata errors, but many of them could be corrected. Anne, I see you looking a little worried. How am I doing on time?
Well, it's actually 4, so
Okay.
we do have some students, so they may exit. I don't know, do we want to open it up for questions?
I'm going to skip the dinosaurs. You can come talk to me later about that during questions and just go on and show you the anomalies. There were, when we got done cleaning it, just in the first 5 years of that program, 151 site years of good data. So I would call it a success. And we found some interesting features that we did not expect. Very strong near surface currents with a high velocity shear. So very strong currents near the surface, and it went to nothing before you were all that deep. Jets with no surface expression, but that were down at 600 meters and more. Strong inertial oscillations at depth. And by way of wrapping up, remember my motivation at the beginning? The most exciting phrase in science is, "That's funny." And that was the reaction everybody had when we started seeing those features in this data that no one expected. Drill ships are big. I told you that. You saw how big our A-frame was. I am near the bow of the ship. That little tiny thing, only halfway back is our A-frame. It is a long way down to the water. And just by way of finishing, this is, I was about to land in Tokyo where I missed a connecting flight, but that's Mount Fuji at sunset. And this is sunset north of Mauritius. And on that note, I am done. I look forward to hearing your questions.
Thank you. That was great. We have a lot of great stories. Does anybody in the audience have a question for Dr. Morrison?
I go by Todd.
All right, for Todd.
I didn't tell you, but I am informal.
Well, that's totally welcome here. Remember, if you have a question, you can raise your hand by going to the participants button and pressing raise hand. In the meantime, I'll ask, you mentioned you had a pretty odd story. I'm a little bit curious about what that was.
Okay, well, this was maybe 6 years ago, and I got a call from the well site leader. This would be the oil operator guy, on a Wednesday morning at the office, and he was just in a panic. And Todd, we can't see any of the data. The system isn't working. You've got to get out here and fix it, and blah, blah, blah. And I just, Mike, calm down. What are the symptoms? I don't want to, just get out here. I said, let me talk with the ET, the electronics tech. No, they've been working on it for 12 hours. They can't do anything. Get out here, please, get out here. I don't think he said please. Anyway, I thought, well, all right, fine. You're authorizing the expense and all of that. I don't know what the problem is, but I can guess. And all you've told me is you can't see the data. So I went home, I packed a bag, put all my PPE in it, drove to Providence, got on a plane. It was delayed 4 hours. I only made it as far as Baltimore. My luggage was in Hawk. I couldn't get at it. Stayed in a hotel for the night, got up early, caught an early flight from Baltimore down to New Orleans, grabbed a rental car. Still hadn't had a chance to shower or change clothes because it was only in New Orleans that I got my clothes. Drove reasonably rapidly to Houma, a town where the heliport is. Left the rental car on the lot, checked in, went through the safety, everything, got on a helicopter, flew out to the rig. Went through the orientation, got my berth, put on took a shower, put on all my personal protective gear, went down to the engine room where our equipment, well, not the instruments, but where the PC was. And I got to the engine room. There's a whole bunch of people down there, and they're all, "Oh my God, Todd, thank God you're here. Can you fix it? How long is it going to take?" And I looked at them, and by now I had a pretty good idea of what was wrong. And I said, "Time me." And I walked up to the rack, and I noticed first that somebody had put more equipment in the rack than when I had installed that system some months or a year earlier. But I pulled out the monitor, observed that it was off, tried to turn it on, wouldn't go on, went around to the back of the rack, found the little rocker switch by the power cord, turned that on, came back around to the front, hit the on button, monitor came up, turned to the assembled masses and said, "Can you see the data now?" That was the monitor connected to the CCTV, but since it was off, the computer did not know how to make a picture. And as soon as I turned it on, it knew how to make a picture. CCTV had an image. No more helicopters that day. I was stuck on board for the night. Took 2 days to get home. So we billed them for 4 days of my time to turn on a monitor.
That is pretty funny. We have 2 questions. The first one, I'm going to unmute Colin Ware, and he's going to be able to ask you the question.
Okay.
Oh, Colin, you might have to unmute yourself.
Okay, can you hear me now?
Yeah.
I can.
Yeah, hi. So I've worked, I work with the data visualization lab, and I've worked quite a bit with operational flow models of various kinds. I'm wondering to the extent to which operational flow models resolve the kinds of features that you're seeing in your data.
Sorry, operational flow models?
Yeah, computational flow models.
Oh, computational, okay.
Yeah.
To what extent do those show these features?
Yeah.
They don't.
Well, I mean, obviously they show big features like the loop current and the...
Yes, you can get that, but you're largely getting the surface. Now, let me add that I am not a CFD guy per se, but I know where they live and I hang out and I get their stories, and I am a numerical methods guy, among other things. So I am aware of the things they are doing, and I will try to be accurate in saying what I do know from them. Yes, you can get to a certain extent loop current-like features. The models, as I understand it, do not show the depth of penetration that you actually measure for the loop current. They also do not predict its behavior well. We do not really understand the loop current. We can measure it. We know that it honks along at a huge pace, but predicting it from day to day, forecasting it, we are not good at yet. Those deeper features, like the jets and the very powerful inertial oscillations, we do not see in models, to my knowledge. Those are something going on that is a head scratching, that's funny moment that people can now study because we know they're there. We didn't know that before. But my understanding is that the models have not replicated that kind of feature at this point. Does that address the question?
Yeah, that's interesting. Thank you.
Certainly gives you something to try for.
We have a second question. It's written in. It's from Roland Arsenal. In what time frame do the big gyres in the GOM form detach and reform?
It's highly variable. There are papers about it. On average, over sufficient iterations in time, I think it is something like a year and a half, 18 months. That's sort of the historical view. Lately, it's been more frequent. But it is not a predictable thing. We are much better at measuring it than predicting it. There have certainly been many cases lately of, well, also historically, but you sometimes see it look like it's about to pinch off and then it doesn't, or it pinches off and the eddy starts away and then they rejoin. I mean, all kinds of funky things happen in the real world. And it's not just that loop current extending up into the Gulf and then pinching off. There are also wiggles over on the West Florida shelf that seem to drive things in an oddly connected way. Things like red tide that you get depending on how things move in that loop of the loop current that is, heading south of Florida. You may get different behavior of the water, not in the loop current, but the water on the West Florida shelf, and other phenomenon come into play that you might not think of. But the loop current is not predictable yet. There is a study going on now from funded by the National Academy of Science, Engineering, and Medicine. We have part of that grant. I mentioned that we had a chance to study the first 5 years of that database and clean it up for a consortium of oil companies. We are now working on the rest of the data up through the current time. And that's part of that National Academy's study. They're trying, I think they decided they couldn't afford moorings, so they're looking at existing data and things like that. A number of academic institutions are involved in that study and are looking at various aspects of it. But one hopes that more will come out of that. I know there are several teams doing modeling and trying to get a better fix on the physics and the actual behavior and things like that. But I am not aware that anybody has been able to predict the loop current to any better extent than our oceanographers who look at, the past several days of measurements and draw their black line about where the 1.5 knot speed is and things, and they make a good educated guess of where it's going to be tomorrow and maybe over the next week. But that's experienced humans do a better job than models right now at that.
Thank you.
Mm-hmm.
It looks like that's it for questions. So I want to thank you again for your time and for sharing all those great stories.
Yeah,
and next
absolutely
week,
my pleasure.
Next week for seminar, we have Dr. Rob Leicester from the UNH Earth Science Department. And with that, I hope you all have a great day.
Thank you all for attending. It's been a pleasure.